Hello everybody, my name is Daz and this is Maths Made Easy. Today this is the second episode of the IGCSE series and I'm going over topic 1.2 sets. So here's everything we're going to cover. First of all, what is a set? So a set is a list or group of things, or we call them elements, the things inside of a set. In math, the things are usually numbers, but they can be other things. And we would like to see the relationship between the sets of things and we'll solve problems with that. That's what the questions are about. So there's also notation, like a lot of notation when it comes to sets. So first, usually what they do is they write the name of the set. So let's say the set of all animals, right, equals, and then you put a curly bracket that looks like that. Then you put an element of the set, so let's say dogs, then cats, then giraffes, and then you would put a ... to show it, like a ellipses to show it goes on. And so that means that the set of animals includes dogs, cats, giraffes, etc. Usually we would shorten the name of sets to just one letter, for example just like A. And sets can also be infinite. So let's say this set of A has all of the integers. So it has -1, 0, 1, and it goes ... in this direction because it goes on forever in this direction, but also goes ... in this direction, which means it goes on forever in both directions. So yeah. We have special names for some sets. For example, for integers, we have like the Z. You don't really need to know that, but it's just nice to know, I guess. I have no idea what that is, just ignore it. Okay, elements of a set, or the things that are in a set, as I explained. And we also have notations to show if something is an element of a set, or if it isn't an element of a set. So let's say there's a set B, right? The elements of a set are 1, 2, and 3. Those are the elements of set B. Then we can say something like 2, and you would draw this kind of E-looking thing, like a C with a line in it. And then B. This means 2 is an element of B. So this symbol basically just means is an element of. But we could also say 5, and then draw this symbol, and then draw a cross through it, and then put B. That means 5 isn't an element of B. So that's notation that you need to know. And there's also notation for the number of elements in set B, or in any set. You would put an N, then brackets, then the name of the set, which in this case is B. And then you would put how many elements are in the set. So here there's 1, 2, 3 elements. So number of elements in B is 3. Yeah. And let's say there's another set, C, and there's nothing in the set. It's an empty set. Well, then we can also write it as C without the N thing is equal to an O with a cross through it. That means that the C is the empty set. This is the empty set symbol. The universal set is a set of all possible things in a situation or a problem or question. Because you can't have everything possible in a question, because then that might not be useful. So they just have a universal set, which this is all that can be. It's kind of hard to understand, but if you have a Venn diagram, yeah, basically. And Venn diagrams is a way to show sets. Here you would have one set as a circle inside this box. That's set A. And then here it's set B. And then everything that's in here is in set B. Everything here is in set A. This part is in set A and in set B. And this part, the outside part, is stuff that is not in set A or in set B, but is still in this box. And that box would be the universal set. It's like kind of this symbol or that symbol. But yeah, it's some Greek letter. So for example, if the universal set was numbers like integers from 1 to 20, right? Say 1, 2, 3, so on till 20. then we know there's 1, 2, 3 in B, 4 in both A and B. So there's 1, 2, 3, and 4 in A and B. Then there's 5, 6, 7 here. Since we know that the universal set has all the numbers from 1 to 20, we can say that outside, that's not in set A or B, has to be all the numbers that are not in here. So we know it's 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. You get it, basically, yeah. But you can't put 21 here because 21 is not even part of the problem. The entire problem only has 1 to 20. 21 isn't even a possibility. So, yeah. See here, it's the same thing I just drew. Universal set, set A, set B. Okay, intersection. The intersection between two sets contains only the elements that are in both sets. This can be shown in the Venn diagram. So for example, if set A has numbers 3, 4, 5, 6, those are the elements in set A. And set B has the elements 4, 5, 6, 7. A intersection B, which is shown with this symbol, it's kind of like upside down U. That just includes the elements that are in both set A and in set B. The only elements that are in both of them are 4, 5, and 6. 3 wouldn't count because it's only in A, and 7 wouldn't count because it's only in B. Only these numbers would be part of A intersection B. This can also be shown in a Venn diagram. Here, you can probably guess, is just this part here. And you would be asked to shade Venn diagrams as part of this unit. In an exam, you would be asked to shade Venn diagrams. So if they ask you to shade A intersection B, just know it's the part where A, literally intersects B. It's kind of easy. The union between two sets kind of contains all the numbers that are in at least one of the sets. So if you think of intersection as and, so the intersection of A and B is elements that are in A and B. The union is like an or, is either an A or B, so it could be in both, but it could also just be in one. So if we have the same situation here, where A is 3, 4, 5, 6, and B is 4, 5, 6, 7. In this case, A union B would be any element that's in either A or B. So 3 is in A, 4, 5, 6 obviously, and then 7 because it's in B. So even though 3 is only in A and 7 is only in B, they still count in A union B because they're in at least one of them. That can be shown on a Venn diagram by just shading the whole thing, like the whole of the two circles here. I'm going to complement. It's all the elements that are not in that set, but like obviously still in the universal set, is shown with an apostrophe. So for example, if A is, again, 3, 4, 5, 6, and then the universal set is numbers 1 to 20, right? 1 to 10, let's say. To 10. And we can say that A complement is all the numbers here that aren't in A, which would be 1, 2, not 3, not 4, not 5, not 6, 7, 8, 9, 10. And this can also be shown on a Venn diagram. So if you want to shade A complement, you just shade everything that's not in this A circle. And this includes, you don't shade the part that's in both either. So you shade everything that's not part of that circle. My shading is kind of bad, but you get it. It's just not in this circle of A. Subsets are a set in which all the elements are part of a larger set. I put larger in brackets because there's like one exception. So basically, if you have a set like A, which is 1, 2, 3, and you have a set like B, which is 0, 1, 2, 3, 4, we could say that A is a subset of B because all the elements in A are also in B. 1 is in B, 2 is in B, and 3 is in B. Which means that you say A, and then the subset symbol is like this, and like a line underneath, B, which means A is a subset of B. Important to note though that B is not a subset of A because 0 and 4 are in B, but they're not in A. And every set has at least 2 subsets, and that is the empty set because it has nothing in it, and that's obviously like going to be kind of a subset of this because it's nothing in here that's not in here. And there's also the set itself, and that's why I put larger in brackets. The set itself is like, it's an improper subset, but it's still a subset, so technically you could still say that B is a subset of B, although that seems kind of wrong because everything that's in B is also in B, obviously. Yeah. So next we have a skill that you need to know, which is shading Venn diagrams. They'll tell you something like A union B or A intersection B complement, or they might put you in brackets A union B complement, and then it could also have 3 sets, like Venn diagrams with 3 circles that kind of look like that, like A union B intersection C. And you have to shade that on Venn diagrams. So I'll show you a few practice questions. Here we have shade A complement union B complement. So what I would recommend, at least to start, is to shade each bit by bit and then combine them at the end. So first shade A complement, which is everything that's not in A here. And then you need B complement, which is just everything that's not in B. Yeah, it's basically everything that's not in the B circle. And then A complement union B complement is, it can either be in A complement or in B complement. So which means just first shade A complement, and then shade also B complement, which is just the out part here. Which means if you kind of put these two on top of each other, the only part that's not shaded is this part. And if you think through that logically, it's the only part that's either not in A or it's not in B, because it's in both A and B. So it's the only one that's in both. Shade A union B complement. So first you just want to shade A union B. Work through it like brackets, like you would do for normal operations. So this is A union B, and then A union B complement would just be everything that's not this. And that's just be the outside part. Nothing of the circles. So yeah. Here. Then finally you have A complement intersection B complement. So A complement would just be, again, the outside part. I'm not going to really be trying to work super hard on the shading, but just lines would be fine. Just make sure they're neater than this. And there's B complement. Everything that's not in B. Yeah, whatever. And then A complement intersection B complement. This is going to be a bit different than A complement union B complement, because it can only be, it has to be in both A complement and B complement. And the only part that's in both of them is the outside part. So yeah. Because this part's not in here, and then this part's not in there, so it's going to be the outside part. Okay, here. 3 Venn diagrams. So here we have to do A, B, and C. So let's start. A intersection B would be just this part. Then you have C, which would just be this whole circle. And then so A intersection B, that whole thing, intersection C. So it's something that has to be in here and in here, and that just be the middle part over here, just tiny little middle part, and boom. Next, A union B intersection C. So again, start with A union B, then C. There's just a circle over here. Then 2 combined, A union B intersection C would just be this part over here because it's in A, unit B, and it's in C. Boom. Sets and logic problems. This is solving for information in sets based on other information you're given about the sets. Usually it's finding the overlap between the sets or the intersection. It's kind of hard to explain, so I'll just show an example. Here. There are 24 people in a class. So, 24 people in the class. 7 like apples, 13 like bananas, and 10 like neither. How many people like both apples and bananas? So, first, right off the bat, we know that the universal set is going to be 24 because that's the amount of people in the class in total. And we know that 10 people don't like bananas or apples. Now, this is the hard part where we have to actually start working something out, is that if 7 people like apples, that means 7 people here in total, right? And 13 people like bananas, that's 13 people here in total. But, I should probably get rid of that. It's 24, 10. But yeah, if that would be true, if we just did 7 plus 13 plus 10, then we would actually get 30, and we wouldn't get 24, which means there'd be more people in the class than there are in the class, which doesn't make sense. That's because we're not accounting for the people who like both apples and bananas. We're double counting them. So what we would do is we just put this as x, right? And then the part that's just likes bananas, that'd be 13 minus the part that likes both apples and bananas. Because that makes sense, because 13 minus x plus x added a whole has to equal 13, because that's how many people are like bananas. And similarly, this is 7 minus x. And finally, we can make an equation by doing 7 minus x plus 13 minus x plus 10 equals 24. So then if we add all this up, 7 plus 13 plus 10 equals 30, and then minus x plus x cancel out with minus x equals 24, which means 30 minus x equals 24, and x equals 6, which means x is 6, this is 1, this is 7, and if we add all that up, 1 plus 6 is 7, 7 plus 7 is 14, 14 plus 10, 24, and that's how many people are in the class. So the answer is 6. 6 people like both apples and bananas. Thanks for watching. Please consider liking and subscribing if you learned something. Comment any questions or topics you would like me to cover, and watch my full IGCSE playlist. Goodbye.